Just a second. Tak. Okay. Right. There. Okay, so welcome to the next Tuesday seminars at the Warsaw University Astronomical Observatory. Today, our speaker is a remote speaker, but with us in real time, Lukasz Tychoniec, who's an ESO fellow. He did his undergrads in Toruń, and then he moved for his PhD to Leiden. And Lukasz is working on ALMA and JWST in the context of chemical mapping of the solar system analogues. So, Lukasz, floor is yours, please.
Thank you very much, Lukasz, and thank you for the invitation. Good afternoon, everyone. Just a little tiny correction at my undergrad in Poznań, but don't worry. My name is Lukasz Tychoniec, ESO fellow, and in this talk, I would like to speak about chemical mapping of the solar system analogues in the making, and in a more general context, how ALMA paves our way for James Webb in terms of observations of solar system analogues. So the research I'm doing is focused on studying of formation of stars similar to our sun. And this means looking at all the stages that happen from the collapse of the molecular cloud that consists of many hundreds or thousands of solar masses of gas and dust that collapses into a single course, or course that will follow multiple systems. But in a simplified picture, we look at the single star that starts to form. And my primary focus is what happens right after that. So after the collapse, we have so-called class 0 and class 1 stage. And this is the first 500,000 years of star formation. But this is actually where the most of the stuff happens. We have a lot of material infalling from the envelope onto the disk, and from disk on the star. We have powerful outflows and opening a wide outflow cavity in this envelope. And then we proceed into class 2, class 3, where we have very well-defined disk. We have little envelope remaining. We have class 3, which is basically a remaining disk. And in the end, we have a planetary system just like ours, and it stays like that for several billion years. So, and all this process lasts only 10 million years, but my focus in this narrow range of first 500,000 years, where indeed all of the action happens, or most of it happens. And to understand how sun and planets are formed, we need to understand, first of all, the conditions that we have at the very onset of this stage and what happens through those stages. So I would like to focus on this part. And there are several important points why it is important to focus on this stage. And that point is that planet formation already starts in this embedded phase. And of course, in the era of exoplanet discoveries, there's a growing need to understand how planets are formed and what determines their diversity, because we see a great difference between different compositions, architectures, and of exoplanetary system. And on this slide on the left, I show an example from my own work, which I did to show that planet formation must start early. I will be looking into this in detail for the first 10 or so minutes. So I won't be going into detail of this picture, but on the right, you see important outcome of this work, or important conclusion, that if we look at planet formation starting early, we need to make peace with the fact that a lot of the physical and chemical conditions that we assumed for planet formation are actually different. And this is the plot from the work of Merel van Hoff, also previously at Leiden University, where she looked at different stages of of disks evolution. And at the earliest stages, the disk is very warm up to a very large radii. This is the radius of the x-axis and temperature on the y-axis. And only in the class 2, in some famous disks such as TW Hydra, we see a decrease in temperature below 20K at relatively small radii. And the 20K temperature is quite important because that's the temperature where carbon monoxide is supposed to be frozen out on the grains already. And temperature above that means that the carbon monoxide is in the gas phase. And now thinking about the planet formation paradigms, whether we form first the solid core or do we have a gravitational instability forming planets, in an instant you can say it for all of those scenarios of planet formation will be very important what is the exact composition of the gas and what is the exact composition of the dust. And just by looking at this plot, it's clear that when we start planet formation is as important as where we start planet formation. So indeed, first, let me take a step back on how we actually provided this important result that planet formation start early. And to answer that question, we looked at the results that's been already in the literature and the discussion that was going on, that when we look at the class 2 systems, so in the mature disks, which are roughly between 0.5 to 2 megayears, what we see there, thanks to ALMA, the large interferometer on the Atacama Desert, which provide us with stunning maps of dust continuum and provide us with robust measurement of the dust mass in those disks. What we saw in all those disks is that the relative masses of those disks are very low, on the order of few Earth masses. And what that means is that it's very difficult to make even a single giant planet in that. So looking at this plot is going to come up several times, so I'm going to explain it right now. What we see on the x-axis is the dust mass, and on y-axis you see a probability of finding disks more massive than a certain value. So for example, looking at 0.5 value of probability, you basically get a median disk mass. So looking at those medians here, we see that most of the clouds that we know to host many of those protoplanetary disks are on the order of several, up to 10, 15 Earth masses, which means that there's a very little mass to form planets. And if you want to form them, you need to form them at very high efficiency. So looking at this a bit closer, there's also a stratification with age. So the young disks seem to be more massive than the older disks. And looking at the approximate mass of the Jupiter core, which is expected to be around 20 Earth masses, it seems that very few disks, as we see them now at the age of 1 megayear or older, are capable of forming even a single Jupiter core. So there's clearly a problem about when to start the planet formation. One of the ideas to solve it is to look earlier and ask whether at earlier stages, at first 500,000 years of star formation, is there enough mass to actually make exoplanets or planets in general. So this is the result from my 2018 work that I've done with collaborators on using VLA array, looking at the masses of the class 0 and class 1 protostars. And what we found out is indeed the masses of those disks are much, much higher, up to order of magnitude higher than what we see in class 2 disks. So looking at the Jupiter core mass, while class 2 disks have large problems making those, you can easily see most of the class 0 and class 1 disks making such a core. So in a sense, we answered to the first part of the question, which means, is there more mass in the early stages? But we haven't quite grasped the answer yet on, is this actually enough to make the exoplanets that we see, not just a one approximate Jupiter size core, but what about the actual exoplanets that we observe more than several thousand to date with Kepler and other missions? So this was another part of this project when we decided to look at the available data set of exoplanets, and we compared their masses with the masses of the youngest disks. But in order to be able to compare apples to apples, we need to, because we measure the dust masses of the disk, we also need to look at the solid content of exoplanets and not at the whole gas and dust mass. So looking at such a gaseous giant such as Jupiter, it has mostly hydrogen and helium envelope, but there's also both solid core, which is mostly made of the dust that has been seen in the disk, but also there's a heavy element envelope, so elements heavier than hydrogen and helium, which will also be of the dusty origin. So it needs to be accreted at some point during the evolution. And in the theoretical work by Daniel Togren et al., the authors provided a very nice solution to how much solid mass or heavy element mass we can expect for a given gas giant. So this allowed us to decompose the masses of planets to a solid mass and to the gaseous mass. And on the other end, we also went back to our data from VLA and refined it with the ALMA data. So basically looking at a bit shorter wavelengths at higher energies. So looking also at a bit different dust, which allows us to compare and obtain the more robust properties of such dust. So in a sense, we also refined the masses of those disks that we measured. And that brought us to the very nice conclusion. We updated and measure very robustly the disk masses in class 0 up to 160 and class 1 around 50 Earth masses in dust can be there. And we plotted in this way that we show in the red and the blue class 0 and class 1 disks respectively, the area which they occupy in this mass space on the y-axis, which show that approximately most of the disks we see have between 10 to 1,000 Earth masses, while the median values are shown in the dashed line there, while in the class 2, the typical median mass is around 2 to 3 Earth masses, so very little. And on top of that, we overplot the masses of the exoplanetary systems, or actually the solid masses of the exoplanetary systems. And we see that they are nicely overlapped with this class 0 and class 1 disk masses, but they're much above what we can expect from class 2, which means that class 0 and 1 disks are enough to produce the exoplanets that we observe nowadays so abundantly. So this indeed showed that the beginning of planet formation occurs already in the first 500,000 years after the star formation process began. And again, that puts an important constraint, and it's very important to understand that we need to study the early stages of star formation to understand the initial conditions to make planets. So having this motivation in mind, I looked into creating a chemical inventory of protostars, basically looking at which tracers, which chemical tracers can provide us with information about which different physical components, because the young systems are quite complicated in terms of different physical components that they are composed of. So indeed, on the large scale, we have the envelope that inflows onto the disk transfers the mass to the protostar, but we also have material that's being ejected from the protostar because it cannot conserve it all with the angular momentum it has. So it needs to release some of it in the form of a jet or a disk wind. And we have also entrained outflow, so basically the envelope that is being carried away with the jet and with the disk wind. And we also have a special area called cavity walls or outflow cavity walls, which is exposed to the irradiation from the protostar, unlike the envelope, which is well shielded from the radiation. But on this area where the disk wind and jet are clearing up the space close to the protostar, there's an area exposed to the UV radiation, which of course alters its chemistry. Also, in the innermost regions, we have a quite warm material. Typically, what we call the material above 100 Kelvin is a hot core or hot corino in terms of low mass protostars. But this is basically area where a lot of molecules are being released from the dust and released from the ices that they are in into the gas phase. And that's why we can see them so abundantly in some of the young sources. And this is most likely due to the thermal emission from the young protostar that's heating up the area around it. An important fact to remember is that in a previous decade, before the interferometric studies of protostars, we looked at mostly looked at those systems with single dish instruments, single dish radio telescopes, and all of those different components were within a single beam. But what we can do with ALMA, with interferometers, is to resolve those systems with the beam of the size of our solar system, so around 50 AU. So we're able to map it with the interferometers. And another exciting part is that we soon are going to get another powerful instrument, powerful telescope that will inform us about the young systems at the early stages. So James Webb, and in particular MIRI instrument, which will observe in mid-infrared, so between 5 to 28 microns, will provide us with many new insights onto the star and planet formation. And just to provide a comparison, the typical ALMA beam, the ALMA that for the observations I used in my work, is on the order of 0.3 arcsecond, which is indeed on the order of solar system scales to a nearest star forming regions. And at the same time, the James Webb MIRI instrument resolution single pixel at the shortest wavelengths that's available will be on the order of similar size to the ALMA beam, which means that we'll be able to directly compare what's in the mid-infrared, so the warmer gas, and what's with ALMA in the colder gas and in the dust as well. But there's one major caveat with James Webb. I mean, of course, it's going to be great and all, but the main limitation is that it's not going to reach the very high spectral resolution. So while ALMA will be able to resolve, is able to resolve features well below 1 kilometer per second, and basically tracing all the fine movements of the envelope and the disk, James Webb will have a typical resolution, looking at, for example, at MIRI instrument of 100 kilometers per second, which means that all those movements will be hidden within one spectral element, and it's going to be pretty difficult to disentangle different kinematic components. So we do need ALMA to guide us into different kinematic components of star formation and of star forming regions, so that we can use MIRI and use James Webb different instruments to understand what we're actually looking at. And this was the goal of my most recent work, where we used observations of chemical tracers to map the kinematics and physics of the protostellar systems to basically set the ground for incoming James Webb observations. And the sample selection we used for the study with ALMA was mostly based on the selected James Webb guaranteed time observation sources. So the sources that we already know will be soon observed with the GTO. And 13 out of 16 sources that we targeted in our work are going to be covered within this program. And what we did, we observed them in 3 different ALMA bands, so being exposing basically to different spectral ranges and at different resolutions, starting from 0.4 up to 6 arcseconds, so being both sensitive to the small scales, to the solar system scales, and also to the entire envelope scales. And in terms of bulk properties of those systems, in terms of bolometric luminosities, which typically gives us a hint on where the star will end up on the end of its formation in terms of mass, they mostly represent subsolar to solar masses. And in terms of bolometric temperature, which is indication of how young is the protostar, they represent both class 0 in red here and class 1 in blue. So the earliest stages of star formation. But it's very important to get a representative sample spanning a wider range of properties of protostars. And this is what we get. And let me immediately cut to the conclusion of this work. So basically what we created was such a map where we use different molecules and highlight which of them can be best used to create such maps of kinematics and physical components for ALMA that can be used to guide James Webb. And I will, in the next part of the presentation, I will look into a bit more detail into all of those components and all of those observations and what we actually found. And you can check the details of each of the specific components in more details in recently published work here. And so let me look a bit into the envelope. So this is the coldest material from all the systems, which is basically still infalling onto the protostar and the disk. And basically the result of The chemistry is being driven by the low temperature and by the carbon monoxide freeze out, because as soon as the carbon monoxide disappears from the gas phase and is being frozen out on the ice, there's a lot of molecules that are not being immediately connected, not immediately merged with CO to create more complex species, but can be seen free in the gas phase. So a lot of molecules that we don't see in the warmer environments are being seen here. And so here I show example of a class 0 and class 1 system. So this is the younger and this is the older system, which show 3 typical tracers of the large protostellar envelope. Let me also indicate that we used here Atacama compact array, which is an array consisting of 7-meter dishes, as opposed to the 12-meter dishes that ALMA provides. And those dishes are typically at much shorter baselines, which means that they have a much lower spatial resolution, but it also allows us to look a bit on the larger scale instead of focusing only on the inner regions, and to basically probe the entirety of the envelope. And what we found is that while CO, or its more optically thin isotopologue C8, is mostly confined to the central region, where it's released of the grains, the N2D plus and DCO plus, so the 2 molecules that are very sensitive to the CO chemistry because they're easily combined with CO in the gas phase, but when CO is on the grains, they can be seen in the gas phase, and therefore provide us with the indication of what is the extent of the envelope. So what we can both see is this approximation of how large are the envelopes of young protostars, and it can range from anything up to several thousand to 10,000 AU astronomical units. And in class 1, we see that this region is much, much smaller, which is consistent with what we already know about envelopes, that its size decreases with age. And also very recently, there's been new work involving also the data that I've used with ALMA to look at those cold gas tracers in much more detail. And in this work, Merel van Hoff showed that H13CO plus, for example, can be well used as a tracer, but not of the CO line, snow line, but of the H2O snow line, so the water snow line. So basically tracing the region where the water is already frozen out on the grains, and H13CO plus, which would otherwise quickly combine with water, can be seen freely in the gas phase. So of course, all those different tracers can be very, very useful in helping us to understand where is the water in such young disks and how the water evolves, how it then is being incorporated into the planetary systems. Looking at a bit of a different part of the young protostar, the one that's been a particular interest to me are high velocity jets. So the material that's being released from the protostar, and it usually provides spectacular images where the high velocity gas with velocities up to several 100 kilometers per second is being very rapidly expelled from the protostellar system. We can see it's highly collimated, and its origin can be traced back to the very inner region of the system, usually within several AU from the protostar. And the chemical origin of this material is very interesting, because what we believe is happening here is that this is not the gas that's being entrained with the envelope, but this is the gas that's being directly released from the disk. And in such, as we call them, molecular bullets, it's being compressed in the shocks, in the internal shocks, and new molecules can be rapidly produced from the atomic gas. And on this image, you can see example of a silicon monoxide, which is usually seen as a classical shock tracer. And this is because why silicon is highly refractory, so it's mostly confined to the grains, but in shocks, it can be destroyed, the grains can be disrupted, and a lot of silicon can be released into the gas phase and will quickly form SiO. That's why we see SiO, so the silicon monoxide, in much greater abundances in the jets and shocks than we typically see in the cold interstellar medium, where most of it is actually hidden into the grains. Protostellar jets are extremely interesting also for other reasons. And this is because what we typically see in their composition is that they are seems to be more oxygen rich than the surrounding large scale low velocity outflow. So this might indicate that the origin of the material is indeed from the very inner regions where the oxygen bearing molecules are already released into the gas phase. So in this case, I first showed some aspects of my previous work where we looked at one particular jet, Serpens embedded 8N, and we saw a formaldehyde H2CO bullet at high velocities. And the kinematics of this bullet, so you can see a moment one map here, where we see that the relative velocity of this gas is up to 5 kilometers per second in this and in that direction, basically expanding bullet. And this is consistent with what I said about the molecules being directly produced in this jet, in this compressed shock. And this is interesting because we typically associate formaldehyde, H2CO, with being a product of the ice mantle. So basically where we have carbon monoxide, CO, frozen onto the grains, it's being bombarded by the free hydrogen atoms and forming first formaldehyde and then methanol. So that's why we primarily associate formaldehyde and methanol with the ice phase production. So seeing formaldehyde here produced in the gas phase is a bit puzzling unless we have grains, dust grains being launched with the jet, and formaldehyde is being released from them afterwards. But this would have very important implications to where is the jet actually launched from, because it will need to be launched from such an area where there is still grains and there are still icy grains, so quite further away from the protostar where it's colder. So this is something we also want to pursue further with ALMA, and it's also been supported by modeling. This is from my colleague Benoit Tabon, who looked at formation of different molecules in such jets, where you have jet basically accelerating, compressed in internal working surface, creating surrounding bow shock. And in this internal working surface, we want to probe many more molecules than already done so far, like CO and SiO, but we also probe methanol and formaldehyde to understand what is the exact origin of this gas. This work also is being motivated largely by the fact that we see many more jets, many more molecular jets currently than we thought we will find. So this is the study of NOEMA. So this is the interferometer that's built in Europe, in the Alps. And so this is the work by Linda Podio et al., where she found with her collaborators that the jets that we see in high velocity in molecules such as SiO and SO are much more common than we thought previously. So she found that above certain solar luminosity, so certain mass of a star, we seem to see quite a lot of those sources. Up to 80% of those sources seem to have such high velocity material. So this means that we can use those sources to try to do a survey of chemical composition of many of those jets and provide more statistically significant and robust conclusions on what is the origin of the gas here. Also, I would like to spend some time to discussing the entrained outflow, so the much slower material that's also being released with the accretion process, as the accretion process is powering the jet and the disk wind, and it carries away a lot of material on its way. And we can see it on this one spectacular case of molecular outflow in Serpens S68N. This is yet another class 0, so a very young protostar. But in contrast to the previous jet that I showed, here we see emission that is at much wider origin, has a much larger opening angle. So that's why we believe it's coming from the more extended area, and it's much slower, which led us to believe that this is the material that's mostly carried away with the faster material from the center, but it carries away a lot of the envelope with it. And what's very interesting is that we found a lot of interesting molecules in those outflows, such as methanol, so the basic alcohol, acetaldehyde, and CH3CN, methylcyanide, and they are all believed to be the product of the ice phase So what we think is happening here is that as the jet and the shock passes through, it released a lot of the material from the grains. And this also opens a very interesting opportunity for us to compare directly the abundances of molecules in the outflow with what is happening in the very inner regions in the so-called hot core that I explained at the very beginning, where the material is not being released due to the shocks, but is being released due to the temperature, where high temperature is basically evaporating all of the ices from the grain surfaces. So this is exactly what we did in terms of comparing the abundances. And we took the abundances of the S68N hot core, so the material from the inner region of the system. This is based on work of Martijn Verhelder and Pune Nazari from Leiden, where they looked at the ALMA data and focused on the very innermost regions of those systems. So basically looking at the very center of this. If you squint your eyes, you can probably see that there's also another peak of material there, where there's a lot of complex organic molecules, and the molecular complexity is actually much higher than what we see in the outflow. So these are the bars where we show the relative composition of different molecules compared with the methanol, which is our reference molecule, which is because it's usually the most abundant one, and also it's usually the starting for all the more complex organic species. And on the red and blue, I show here the abundances of molecules with respect to methanol that we see in the red shifted and blue shifted part of the outflow from the same source. So when you think about it, that initial envelope has a reservoir of ices that's being then collapsing, creating a disk and the protostar. In principle, we should see a very similar composition of the material, whether it's released thermally in this, close to the protostar or further away in the outflow, unless some of the processes are happening differently in the outflow in the shock regions and close to the protostar. And the discrepancy that we see for those two molecules, this acetaldehyde and ketene, might be the result of just that, where we see a large enhancement of those two molecules in the outflow. This can both mean that the molecules are efficiently produced in the shocks, has been also showed in other works that this is possible, or that those molecules are more easily destroyed by the temperature in the innermost region of the protostar. And this, for the case of acetaldehyde, CH3CHO, has been also shown in a recent work by Marta de Simon and collaborators, where she showed that for the scale is inverted here. So where I compared acetaldehyde to methanol ratio, she compares otherwise. So, but you can think about it that it's greatly enhanced. The acetaldehyde to methanol is greatly enhanced in outflows and shocks compared into the hot core, so HC being shortcut here for most of the systems. So indeed, this seems to be robust across many different sources. And in principle, this is a very new avenue which opens up a possibility to directly compare the abundances in the outflows and the hot core regions. And I think we need much more ALMA studies on those systems. I would like to also briefly discuss cavity walls. So as I mentioned, the material that's, because it's being exposed to the UV radiation from the protostar, it has a quite interesting chemistry. So we can probe this material with molecules that are usually associated with from so-called PDR regions, so photon-dominated regions or photodissociation regions, where because of high UV field, there are particular abundances of molecules that would be otherwise not very stable. So for example, or not very abundant. So for example, we see here a CN, which could be a result of UV enhanced production of this molecule and its interactions with molecule hydrogen and ionized hydrogen. And we see also C3H2, which is most likely a result of a combination of the ionized and neutral carbon with hydrogen. So all of those molecules usually need a reservoir of free atomic gas. And atomic gas is usually a result of photodissociation from the UV radiation. And we see a very interesting shape. So if you look at CO, so carbon monoxide is basically seen everywhere because it's very abundant. It's the most abundant molecule just after the molecular hydrogen. We see it tracing the bulk of the outflow material. But those UV tracers we see usually confined to this narrow area, kind of a V-shaped area close to the source. So this kind of indicates that those molecules can be only traced very close to the protostar, where UV radiation would be strongest and then would be decaying with square distance. But very close to the protostar is going to be high enough to actually ionize this molecule. And this is very important information because that means that UV irradiation is also important for solar-like stars when they are forming, and then can be very important for the formation of more complex molecules, for molecules that would require a high energetic radiation to be formed. And we have nice tools now to probe those regions with such molecules. This is the case for another source, another class 0 protostar, where you have highlighted in those black dashed lines where the outflow cavity wall is. So where is the edge of the material that's being exposed to the radiation? And we also have the SMM3, which I already showed, and the outflow directions also seen here. So clearly we can use those molecules to not only look where the ionized material is, but also to quantify the levels of radiations in the future with more tracers. So in order to summarize, this is again a whole overview of the sources that we looked at and of different chemical components that we looked at. And in the remainder of the talk, I would like to focus on how this result applies for James Webb Space Telescope, which is due to launch in a month from now. So let's take a look again at the instrument that's of most interest to me and of most interest to the early star formation studies, which is MIRI, mid-infrared instrument. And we can see that within 4 channels, looking at slightly different wavelengths, each of them, from 5 to 28 microns, it will have a field of view of several, starting from 3 to 7 arc seconds in one of the directions. But its actual resolution, I also mentioned, will be sub-arc second scale. So we'll be able to have spectra of each of the pixels. And let's discuss for a moment what will be different between ALMA and James Webb. It's not only the different wavelength range, but also because of the different wavelength range, we're looking at very different chemistry, very different processes, because where ALMA mostly focused on a bit lower energetic stuff, on the cold envelope, on the entrained, so non-thermally released material in the outflow, a bit more energetic jet, but still rather a byproduct, the cold molecular gas that's being the result of it. And in terms of innermost regions, it's mostly traced the gas that's being already released from the grains. The James Webb will give us a unique look at more energetic processes. So for example, looking at the cavity walls, it will be tracing shocks where the water and OH radical is being produced. It will show us a more atomic and ionized gas from the jet and the outflow. And this will be highly complementary to what we are trying to find in terms of molecular composition of those jets, because we believe that especially as source evolves and more jet material is being exposed to radiation, those jets become mostly atomic and mostly ionized. And therefore, we really need those data at different different stages to complement ALMA and to understand how those chemistry is evolving in those jets. In terms of innermost regions of the protostar and the disk, except for tracing disk atmosphere with ionized oxygen, H2, CO2, various different molecules, also water in the disk, as it emitting in the gas phase, we'll be also seeing very important part, which is ICES. The shortcut here, COMS, means complex organic molecules. So we are really hoping to observe some of the complex species, basically the prebiotic species, not only in the gas, which we already do with ALMA, but also in the ice. And in that sense, we'll get a complete picture of the chemical reservoir of the planet-forming material. So let me look a bit closer at several specific sources that we already observed with ALMA, and we are waiting eagerly to observe them with James Webb. So this is one of them. This is Serpens SMM1, one of the more massive protostars, which probably will produce a star of at least 2 solar masses. And what we can see here is that it's actually binary system well, if you look closer, it's actually a quintuple system, but let's not focus on such details. We have two, at least dusty components here seen in the black, and contours show ALMA data. In the red, the high velocity jet above 35 km per second, as traced by carbon monoxide. And here we see in black contours, we see colder envelope seen at very low velocities from 2 to 6 km per second. So keep in mind that all of those different velocities would be captured within a single spectral channel with MIRI, with the James Webb instruments. That means we won't have resolution to decompose them, but we do have spatially and spectrally with ALMA. And knowing which chemical tracer corresponds to which physical component, we can understand very well what's happening in those systems. And now what you see in the green is the MIRI MRS footprint. So one of the instruments, mid-infrared instrument, will look in that system with those two footprints. So we need two integrations on each of these parts to cover the extent of the envelope and also the part of the jet. Of course, we would like to do a whole suite up to large scales of this jet, but those observations are very expensive and very time consuming. So we want to focus on the protostar here. And each of these pixels here, because of the design of the MIRI instrument here, each of these pixels will provide us with a spectra from 5 to 28 microns, therefore providing us with spectral images of such systems. And thanks to ALMA, we'd be able to directly pinpoint which physical component is corresponding to which spectral feature. So for example, we expect to find a lot of ionized lines here in the spectra here, and we expect to find a lot of ices in the absorption on the contrast of the protostar here closer to the system, and perhaps the disk features also overlapping on this source here, and perhaps even spatially resolved with several pixels mapping the area here. Another interesting case is TMC1. This is a class 1 system, so it's a bit more evolved, which we recently found to have this very interesting kind of filament feature, which is very narrow and also very low velocity, which we can associate with material still in falling from the envelope and feeding the disk even at later stages when the bulk of the accretion is almost over. And again, with James Webb, this is now the full footprint without each of the pixels showed. Now we can see, we will be able to also look how it looks in the infrared, and particularly if we can see any hints of the accretion shocks as the material from the envelope falls onto the disk. And the last two sources I want to showcase, one of them is BHR71. This is a class 0 protostar. When we decide to be a bit more ambitious and do a whole mosaic of the outflow, seen here with ALMA, and we do a 3x3 mosaic, so we'll be able to cover a much larger extent of the outflow, basically looking how the shocks, how the UV radiation are impacting the environment up to here. And again, on top of that, each of the pixels that you see here in tiny red green circle, green squares will also show us spectra, each of those pixels. And one other source that I want to highlight, B1C, is a class 0 protostar. And this is the source that I described where we already have gas observations from the works of PhD students in Leiden. And we also have laboratory data also from the Leiden laboratory, where we will be able, in case of this source, directly compare what's happening in the gas phase with what's available in the ice. And with that, let me move on to conclusions. So coming back to the very beginning of the talk, planet formation really starts early, which also means we need to focus on the early stages of star and planet formation to understand what are the starting conditions for making planets. It's clear now also that James Webb and ALMA will deliver very powerful synergy, and we need both of those telescopes to actually answer some of the fundamental questions of star and planet formation. I also showed that Protostellar jets chemistry promised some insight into what's happened in the innermost region of the disk, so basically where the jets are being launched from. And also I showed some comparisons between chemical complexity in the outflow and what happens in the inner envelope, where the molecules are released from the ice grains. And we can, from this, we can try to compare them and understand some of the formation routes for the complex organic molecules. And with that, I would like to conclude and thank you for your attention.
Okay, thank you very much, Lukasz. I'm afraid the microphone, the only one I have, is not working. So if you have questions here in the room, please come forward. Elena. You could come closer, then the question will be heard. And you will be seen in the camera as well.
Hi, Lukasz. Can you hear me?
Yes, thanks. Hey.
Nice to see you. Thank you for a very nice talk. I have a question regarding merger of protostars. So actually, are there any, well, what kind of behavior of given tracers that you described could prove that we observe the merger of protostar?
Oh, you mean the merging of protostars at very early stages, right?
Yes.
That's interesting. I mean, as I showed at the very beginning, we, in some sense, we are very ignorant, saying, okay, this is our spherical cow, this is our protostar, single protostar, but this is of course not the case. And we've seen, I think one interesting aspect could be some kind of explosive accretion, as we are seeing. There is a famous case of Orion KL, I think, where basically with ALMA, they showed several filaments basically going outwards. I would guess this could be a case of such a merger, right? When we see some very clear disturbance. But I think most of these things could be also occurring in much more quiet mode. For example, as accretion outbursts, right? Because maybe it's probably difficult to think what would be the sign of very massive two stars merging. And that's also out of my area expertise. But at the early stages, what we believe is happening is that even the young planetesimals or even small clumps of matter will not be falling like constantly in a continuous way on the protostar, but falling in such a clump. So I could imagine just a scaled down version of such clump falling onto the protostar. What we then see is increasing temperature up to a large radii. Of course, then in infrared or invisible light, we can even see it outbursting. That's what we call FUO resources in the young protostar systems. And in the earlier stages, what we usually do is we try to infer it by chemical composition. So for example, we see the carbon monoxide being in the gas phase to a much larger area than would be currently expected from a temperature of the protostar, which might mean that previously in the past, something happened that increased the temperature up to a larger radius. So I would think about such small things. But of course, I think on the other extreme, there are those powerful events that could be resulting in massive explosions, basically, of the material.
But as far as I understand, that doesn't happen really often, right? I mean, like...
No, I don't think so.
There is only one case or something that you mentioned.
Yes, yes. I think it might be also very early, it might be difficult to distinguish those with just regular accretion happening, right? As I said, this will be just a material falling in, and I'm not sure what would happen differently. And also, I'm not sure how stable those systems will be at the early stages, right? When you have two very close protostars where they would stabilize in very efficiently and then form a tight binary system, or they will just merge in a maybe non-violent way. But yeah, that's out of my expertise, sir.
Thank you. Thanks for clarification.
Any more questions here? Marcin, please come forward. At least here, sir.
Hello, thank you for your excellent talk. And I have a question. What are the most massive stars observed by ALMA during formation?
Oh, I mean, there are a lot of studies with ALMA devoted to the very massive stars. So I think they range in up to several thousand of solar luminosities. So we can expect them that will clearly end up on the main sequence as a massive stars. And yeah, I'm not actually sure what the limit is, but it's probably very high, because the problem with those massive star forming regions are, of course, that the formation of massive stars is much rarer thanks to what we know about IMF. So we also usually need to look much further away to form them. And then they also occur in much more dense clouds. So we usually don't look at, I mean, nowadays we already have studies of several of those high mass star forming regions resolved that we can look at separate cases. But it's still much rarer than what we now have this luxury of looking at dozens of low mass sources. But I'm not sure of the upper limit of that, but there are definitely studies of high mass sources with ALMA.
And I have a question. Are there any signs of planetary formation in high mass stars?
Yeah, that's a very interesting aspect. And I think now we are quite sure that we have at least some of the massive stars with a disk. There are, of course, several different problems with formation of disks and then planets around those massive stars. First of all, the radiation and the relatively short timescales for a formation, because even in our low mass protostars, the major limitation for making planets later on is that as the material dissipates and the envelope dissipates, they are exposed to the both internal and external UV radiation, which will basically dissipate the gas. So it will be very difficult to make, for example, a massive planet. And in terms of high mass protostars, this will happen much, much quicker, and both from the inside and in the outside. So I think there are certain limitations to that. So in terms of planet formation, I wouldn't be too optimistic, but we start observing some disks around massive stars. So I think it's still to be explored.
Okay, any more questions here?
Hi, Lukasz. Thank you for the nice talk. And I have a very general question, but you have mentioned 50% efficiency when forming planets in early disks. And what are the processes that curb this efficiency? Because I presume that would be these gas outflows, or am I wrong about that?
Yeah, that depends on the mechanism that you assume for the formation of planets, but assuming the most general paradigm, which is pebble accretion. So what you start with is basically gaseous and dust disk with a fairly standard gas to dust ratio of 100. And what will happen in this paradigm is that you have at certain point the streaming instability, which will trigger formation of planetesimals up to several tens of Earth masses sometimes. So basically cores of solid planets. And then what would happen if it's massive enough, it will start accreting more gas. So at each of the steps, the efficiency will be limited by several different aspects. For example, in terms of pebble accretion, which means that when you start creating one planetesimal, then to grow to actual planet, rocky planet, it assumes that the planetesimal will cross on their orbit many of the pebbles, many of the smaller pieces that will emerge into it. And this process is very low efficient, as you can imagine, because most of the pebbles actually drift closer to the protostars, they evolve. And basically, planetesimal must be lucky enough to encounter them. So the efficiency of this process is usually expected to be not more than 10%, which means that we have a 100 Earth masses disk. Only 10 Earth masses will end up in such planetesimals. And in terms of the gas accretion, the primary limitation is in the context of what I mentioned in terms of high mass stars, there are photoevaporation of the disk. So with time, when the gas will start basically disappearing from the disk because it's being exposed to the UV radiation.
All right. Okay. Thank you.
Great. Any more questions here? I just have a quick one. The jets, I'm really impressed by the sizes. The scale you show on your pictures are hundreds of AUs. So these jets, they're very fast. So you know, I'm familiar with jets in AGNs and black holes and so on. But here the question is, because it's a star forming. So what is can you kind of accumulate, integrate over time the mass loss due to jet in this star formation? What's the fraction of mass, or you know, how long these jets live, and you know, how much mass is actually spit out during the star formation?
Well, as we know, the star formation process is not very efficient. Like what we usually observe from the core mass function to the initial mass function is on the order of 30% efficiency. So the rest of it is either expelled or basically not ended up in the star itself. And majority of that we believe is due to the outflows. And so the jet stars very powerful. They usually in the class 0 can reach 10 to minus 6, 10 to minus 5 solar masses per year. This is very efficient, and it's usually on the order or slightly lower than the mass accretion rate onto the protostar. So, and of course, this ratio sets up your final efficiency of the star formation. But indeed, there's a lot of mass being released from that with that process.
Okay, cool. Thank you very much. I don't see any more questions, so let's thank our speaker again. Thank you, Lukasz. Thank you, everyone else, for joining us, and stay tuned for the next seminar. Bye-bye.
Thanks a lot. Bye.